At least. I mean, I have to keep one mic off of you. Congratulations.
All right, well, welcome to the end of 215. So, any questions before we just kind of go through a general review?
Double-sided, she's double-sided, 5 species.
Correct.
Single-sided
Yep.
again.
Mm-hmm.
When's the final?
Good question. When is the final? I believe it's Monday at 12.
Yeah, Monday.
So if you take the 224 exam at 10, you can do 4 hours of final exams. Double your fun.
I have that on Wednesday.
Hmm?
I have that on Wednesday.
Yeah, on Wednesday.
Calculus and tennis that we'll take that.
Oh, fun. Yeah. All right, other questions? More questions?
We go over induction.
Yeah, absolutely. Because there will definitely be at least one induction question on your final. So, what's the general concept behind mathematical induction? It's recursive. What does that mean?
If you have a base case where it's true, you can extrapolate that to all cases.
Okay, good. If you have a base case where some proposition is true, and you have a way to move from one case to the next, you can start at the base and you can keep applying that step and move up to any number that you want if we're inducting on numbers, right? So if we know, say, P of 0 or P some proposition, right? If we know P of 0 is true, and if we're given that if P of n is true, then P of n plus 1 is true for any n bigger than or equal to 0, then we can conclude that P of n is true for all n bigger than or equal to 0. And it's not very mysterious, right? Is P of 5 true? And you don't know anything about mathematical induction, but you still are given these things, right? Well, we know P of 0 is true, and we know that P of 0 implies P of 1. If Q is true and Q implies R, we can conclude R. That's direct reasoning, right? So given P of 0 and given that P of 0 implies P of 1, we can show P of 1 is true. Well, we're given that if P of 1 is true, then P of 2 is true. And so direct reasoning again gets us P of 2. And we keep doing this until we get to P of 5, and then we say, yes, P of 5 is true. Right? So we don't need induction to prove P of any particular n bigger than or equal to 0. The only thing induction is doing is it's letting us do this ... formally. It's letting us say if n is any number bigger than or equal to 0, we can follow this chain of reasoning and eventually get to concluding that P of n is true. Okay, so it's a formal wrapper around something that we already know intuitively, which is we can start here and we can keep taking steps until we get to P of whatever we're after. So you got 2 steps, 2 pieces. This is your base case. And this is your inductive step. All right, so let's pick an example, which hopefully is not on the exam. It could be. It's a weird question for a mathematical induction thing. I'm not sure what that's doing in there.
Me neither.
That sounds like a chapter 4 question. Those look harder than I want to do. Let's do something from 3.7 directly. Okay, this one looks nice and gnarly. Let's try this one. 1 over 1 times 2 plus 1 over 2 times 3. Up through 1 over n times n plus 1 equals over n plus 1, n bigger than or equal to 1. Alright, so let's try to show this using induction. So what's our first step? Say again? Even before we make a base case.
Proposition.
Proposition. Alright, so let P of n be the proposition. Alright, so I'm just rewriting that. P of n is the proposition, so that's a declarative statement that the left side is equal to the right side. It has a truth value. So now we can do your base case. P of 1 says 1 over 1 times 2 equals 1 over 1 plus 1. And both of those sides are equal to 1/2. So that's definitely true. So P of 1 is true. Okay, now for the proofy part. So assume P of n is true for some n bigger than or equal to 1. We want to prove P of n plus 1. Well, P of n is true, so we can write this. Right, we know that's true because that's what P of n says, and we're assuming P of n is true. Well, we want to prove P of n plus 1. And P of n plus 1 says something almost exactly the same. Right, we're just going to add one more term on the left here, 1 over n plus 1 times n plus 2, and that should turn out to be equal to n plus 1 over n plus 2. That's what we're after. If we can show this without cheating, right, then we've shown P of n plus 1 is true. Right? So sometimes this is weird, right, because we've got an n and n plus 1 and so on, but you could use a different variable if you want, right, if it gets confusing. But basically, we're doing this for something one number bigger than n, right, which means this is going to be n plus 1, this is going to be n plus 2, this will be n plus 1, this will be n plus 2. So we've already got this. We want to get this. And a lot of these problems with math equations, it turns out we can turn part of this into part of this by just adding something, right? It's not clear how to turn n over n plus 1 into n plus 1 over n plus 2. But if we work on the left sides, we can take the left side of this thing, which we know is true, and if we just add this one term, this whole left side is going to look like this left side. Okay, that doesn't prove anything, but it's a suggestion that maybe we should try just adding that to both sides. So now I'm going to say 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over n times n plus 1 plus, and I'm going to add one more term, to the left side. And if I want to preserve this equality, and I got to write down things that are true in proofs, I've got to add this thing to the right side also. Okay, nobody can argue that that's a true statement, because the statement before is true, and I've just added something to both sides. And now we're just going to go crazy with algebra, and we're going to clean up this right side. And so I'm just going to write an equal sign, hopefully right underneath that equal sign, but I drew a squiggly. So, so how do we combine these? Well, let's multiply the top and bottom of the first thing by n plus 2. So n times n plus 2 over n plus 1 times n plus 2 plus, and I'll leave the second term the same. And then I'll clear some terms. Oh, this looks a little horrifying. Yuck. That's not what I wanted. Something weird in here. You got it.
Can you just factor the top, and then it'll be n plus 1 times n plus 1 over n plus 1 times n
Oh,
plus
thank
2.
you, thank you. Okay. I was freaking out. Test anxiety.
That's exactly what you want to get to.
Yeah. All right, so factor the top one, and then just cancel the n plus 1s, and you get n plus 1 over n plus 2. All right, so now we've shown that this whole sum is equal to this. And now we simply note that that's p of n plus 1. Therefore, p of n implies p of n plus 1. Therefore, p of n for all n bigger than or equal to 1. So that's pretty much what every inductive proof looks like in some form or another. Now sometimes it's some expression, usually a summation or a product, is equal to something. Sometimes it's an inequality, right? Show that I don't know if they have inequalities they did before. Show that n factorial is bigger than n squared, right? Sometimes it's something about divisibility, right? Show that this is a multiple of 5 for all n. Sometimes it's something weird with people shaking hands. I won't do a weird one on you. But in all these cases, your steps are the same. First, decide what it is you're trying to show. We're trying to show that, you know, every person is named Jerry. Okay, so make a proposition from that. Let P of n be the proposition that in a room of n people, they're all named Jerry, right? Somehow turn this into a family of propositions. In a base case that's true, write down your inductive step and then go about trying to prove your inductive step. And once you've proven P of n implies P of n plus 1, put it all together, right? Therefore, P of n for all n by mathematical induction. So how do we do that handshake one? That looks interesting. Suppose there's n people in a room, they all shake hands with one another, prove that n times n minus 1 over 2 handshakes will have occurred. Any ideas? What's our proposition?
Our proposition states that n times n minus 1 over 2 handshakes.
Yes. So the proposition sometimes comes straight out of the problem. Sometimes you have to wiggle it around a little. So in a room with n people, there are n times n minus 1 over 2 handshakes. That's a little poorly worded, but what the problem said. So what's a good base case? This is n bigger than or equal to 1. So P of 1 says
There will be no handshakes.
there will be no handshakes, right? There's 1 times 1 minus 1 over 2 equals 0 handshakes. And that is correct. If there's one person in a room, you don't shake hands with yourself. Nobody shakes hands with anyone, right? So P of 1 is true. Okay, assume P of n for some n bigger than or equal to 1. So you got n people. We have n times n minus 1 over 2 handshakes. Okay, how do we prove P of n plus 1? How do we find how many handshakes there are if there are n plus 1 people in the room? Probably by using what we just know, what we just learned about number of handshakes with n people in the room. Right, so if there's n people in the room, there's this many handshakes. Now we've got a room with n plus 1 people. How many handshakes are there? Well, we can do this by putting n people in the room first, letting them all shake hands, which will be this many handshakes, and now send in your n plus first person and do whatever handshakes need to happen. Well, the only new handshakes that need to take place are this new person shaking hands with everybody who was already in the room. So, number of handshakes for n plus 1 people is the number of handshakes those first n people do when they all shake hands with each other, plus this new person goes in, they have to shake hands with n people, right? The people who are already in the room. And that's it, right? Everybody who's in the room has already shook hands with each other. New person comes in, shake hands with each of the n people, and now everybody is shaking hands with everybody else. So given P of n, this is the number of handshakes for n plus 1 people. And now you're at your algebra section. And we rearrange it and we get n plus 1 times n over 2. So assuming P of n, we've just shown that n plus 1 people shake hands this many ways. And that's P of n plus 1. Therefore, P of n implies P of n plus 1. Therefore, P of n plus 1 is true for all n bigger than or equal to 1.
Never mind.
Okay. All right, good. All right, other questions?
Can you go for proofs?
Proofs, yeah. We just did some.
Oh, version.
Say again?
The indirect.
Direct and indirect, yes. All right. So let's see. So let's prove that if n is an odd number, then n cubed is an odd number. So let n be odd. There exists an integer k such that n equals 2 times k plus 1. Or we could say just n equals 2k plus 1 where k is an integer. Right, so let n be odd, that's an assumption, or a hypothesis. This is the definition of odd. So n cubed equals 2k plus 1 cubed, which is 8k cubed plus 4k squared plus 2k plus 1. That's algebra and substitution. And then I'm just going to factor out a 2 from part of this. And that's more algebra. And now we just note that this is 2 times some j, which is an integer, plus 1. Right, because we know an integer cubed is an integer, and 4 times an integer is an integer, right? So that's where I just kind of generically say properties of integers. But I'd be fine if you didn't even list a reason there. So n cubed is equal to 2 times j plus 1, therefore n cubed is odd. And that's the definition of odd. Because it's twice an integer plus 1. So we use the hypothesis that n is odd, and we prove that n cubed is odd. That's what we wanted to prove. So there we can say QED. All right, so let's do an indirect. Let me see if I can think of a more interesting one. I don't know, maybe not. Let me make sure this is true. Okay, I think that's true. If we can prove it, then it's true. This still looks really fuzzy to me. So prove that if n squared plus 8n plus 1 is odd, then n is even. And if we try to set this thing equal to 2 times k plus 1, we don't really get very far because the square is going to trip us up. So this will work better with an indirect proof or a proof by contradiction. So assume our hypothesis n squared plus 8n plus 1 is odd. That's the hypothesis. And then assume n is odd. That's an assumption. Right, so we're assuming the opposite of the conclusion, we're going to find a contradiction. So n equals 2k plus 1. N squared plus 8n plus 1 equals 2k plus 1 squared plus 8 times 2k plus 1, which is 4k squared plus 4k plus 1, plus 16k plus 8 plus 1. Don't panic at this point. Just keep going. 4k squared plus 20k plus 1, 9, 10 factor. Which is equal to 2 times j, where j is an integer. So n squared plus 8n plus 1 is 2 times j. Therefore, n squared plus 8n plus 1 is even. And there's our contradiction. Because we assumed n squared plus 8n plus 1 is odd. Right, so this is a hypothesis. This was a random assumption, and we got to a contradiction. So our random assumption must have been wrong. Right, therefore, n is not odd. Therefore, n is even. And that's what we wanted to show. So in general, prove that P implies Q. Well, there's two ways to do that. A direct proof does the following. It starts with P, and then it finds things that follow from P until eventually it finds Q. Okay, it's a direct proof. It's direct reasoning. We've shown that if P is true, then blah, 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 blah are also true, and therefore Q is true. So if P is true, then Q is true. That's exactly what this says. The other option is basically assume the negation of the conclusion, show things that follow from that until you eventually show that P must be false. But this is a direct proof of the following, right? Not Q implies not P. Because we assumed not Q, we argued logically, and we eventually came to the conclusion not P. So an indirect proof of P implies Q is really just a direct proof of not Q implies not P. But once we've proven this, we can take the contrapositive, which is logically equivalent, and say, therefore, P implies Q. So we're changing our original problem for a different problem, and then we're doing a proof of that different problem. But what we're proving is basically the contrapositive of what we wanted. And so it's equivalent to proving the original statement. Absolutely. Have I done the birthday cake analogy yet for functions? Let's try this. Let's see if it works. Sometimes it does, sometimes it doesn't. So a function is a map from one set of things to another. Okay? So here's one set of things. These are students in CSE 215. And the thing we're mapping to is a pile of cookies. And F basically takes each student and assigns to them a cookie from the pile. Okay? There's Alex's cookie. All right, so there's different types of mappings that we can have. So if each student gets their own cookie. That's injective. So injective means that different points over here map to different points over there. It's not the case that you have 2 points here mapping to the same point. Okay? So if 2 students have to share the same cookie, it's no longer injective. Okay? Injective is also 1-to-1. Okay, so injective or 1-to-1. So different points here map to different points there. That's injectiveness. Surjectiveness means every point over here gets mapped to by something. In other words, all the cookies are claimed. So, if each cookie is claimed, that's surjective. And those are independent of each other. Okay, surjective is also onto. Right? You might have a single cookie over there and everybody gets mapped to it. Okay, that's the most non-injective function possible. Everybody's sharing the same cookie, but it is surjective. It's onto because every cookie is being mapped to. On the other hand, you could have a trillion cookies over here and 23 of them will be mapped to from students. It might be injective, might not be, but it's not going to be surjective. Right? There's points over here in the codomain that are not mapped to from anything. Okay? If it's both injective and surjective, that's bijective. So bijective is 1-to-1 and onto. And that's basically one student, one cookie. Okay, if you have 23 students, you got exactly 23 students, 23 cookies, and each student maps to exactly one cookie and vice versa. Okay, so injective points are mapped to from no more than one place in the domain. Surjective, they're mapped to at least once, and bijective, they're mapped to exactly once. Okay, in cookieology, injective means that every cookie is taken by no more than one student. Surjective means every cookie is taken by at least one student. Bijective means every cookie is taken by exactly one student. Does that make sense? If it's bijective, right, student cookie, there's a 1-to-1 mapping between students and cookies, and every cookie is allocated for, then we can reverse the mapping. I can say, here's a cookie, tell me which student goes to this, right? You can't do that if it's not injective and surjective. If there's cookies that aren't mapped, then our inverse function isn't defined, right? Nobody wants the coconut broccoli cookie. There's no map to it, so we can't define that inverse mapping, right? Or if 2 students are mapping to the snickerdoodle, and we say, okay, which student does the snickerdoodle map to? Well, it maps to 2 different students. That's not a function. It fails that vertical line test from calculus, right? So it's 1-to-1 onto tells you that you've got an invertible function. I don't think I asked you about this on the test, though, so you got it anyway. All right, what else?
Use a product and sum rule.
Yeah. So T is some task you're trying to perform. So if T can be done by doing T1 and then T2 and so on up through Tn. Well, let me simplify it. If t can be done by doing t1 and then t2, right? And t1 can be done n1 ways. And t2 can be done n2 ways. Then t can be done n1 times n2 ways. So things in succession, we can multiply the number of ways to do each piece, and that gives us the number of ways to do the original task. So if you want to make a sandwich at the salad bar and you have to choose a type of bread and you have to choose a type of meat and you have to choose a type of cheese. So the number of breads times the number of meats times the number of cheeses, that's the number of ways that you can complete this task of picking a salad. Right? It's the product of the number of ways to do each subtask, so that's product rule. And then the sum rule, basically t can be done by doing t1 or t2. And so the number of ways to do t is n1 plus n2, where n1 is the number of ways to do t1, and so on and so forth. So you're required to pick either a soup or a salad. There's 5 soups, there's 7 salads. You have 12 possible ways that you can answer the question, what do you want to eat? Right? Because you can decide I'm going to get a soup and I got 5 ways, or I can decide to get a salad and I got 7 ways. Right? Now if I had to pick a soup and a salad, there'd be 35 ways. Soup 1, salad 1, soup 2, salad 2, etc. And this may wiggle your brains a little if you think about this in terms of when we can do a task by either doing T1 or T2, right? That's a logical OR operation. When we do it as a succession, right, then we're doing T1 and we're doing T2 and T3 and so on and so forth. And with the ands, we have a product, and with the ORs, we have a sum, right? And this is, you know, not coincidentally the dot and the plus that we get in 250 when we do logical operations. We call it a product of sums or a sum of products, right? Those things, right? It's the same thing. Just like when we do an AND, right, that goes along with an intersection, and when we do a sum, that goes along with a union. And an intersection means that an element is in this set and that set. A union means it's in this set or that set, right? There's the AND and the OR again, right? So this is all the same stuff that you've been doing since CSE 120. It just shows up in different forms, right? But it's all still the same basic Boolean operations. That keeps happening.
Can we do an example of them together?
Sum and product? Okay. So pick a password or 2 security questions. So your password has to be 5 letters. Or 2 security questions from a list of 7 questions we'll let you pick from as we build up our dossier on you. So authorizing yourself to the system, right, setting up your account at HackMe Incorporated requires you to do either this or this. Okay, so how many ways can you pick a password of 5 letters? Well, to pick a password of 5 letters, you got to pick the first letter, the second letter, the third, the fourth, and the fifth, right? And there's 26 letters to choose from for the first. And since we allow repeats, there's 26 for the second and the third, fourth, and fifth. So that's the number of ways we can pick a password of 5 letters. if you want to pick 2 security questions out of 7, well, the first security question, you've got 7 choices, right? What's your favorite color? What's your quest? Whatever. So you got 7 ways to pick the first security question, and then you'll have 6 ways to pick the second security question, because you can't repeat. So the product rule tells us there's 26 to the 5th passwords, and it tells us there's 42 ways that you can choose 2 security questions. The number of ways you can set up your account is the sum of those, right? Because you can either do that first method or that second method. So how many people, like, honestly fill in security questions with, like, real information? Okay. I used to just bang on the keyboard and, you know, be done with it, because I don't forget passwords usually, right? And then I tried to log in somewhere, and I hadn't logged in like 2 years, and they're like, whoa, we have to check your security questions first. And it's like I had no idea what I had typed. I think it was my Yahoo account, actually. So I've got a Yahoo account that's, like, ancient, with email just piling up in it, and I have no way to get to it. So now I just put down snarky things like, you know, class action suit, stuff like that. All right, does that help?
Yeah.
Cool. All right, what else? Permutations, combinations. Cool. So permutation of n objects. So ordered or unordered?
Ordered.
Is that a guess? Yeah. Can't guess because I don't remember. I was hoping everybody would say the same thing. Then I could pretend I actually, like, know this stuff. Permutations are ordered. That's why it says ordered on there. So when I'm going through this, I don't have to remember. So permutations are ordered. So the number of ordered arrangements of n objects. And we can find that number by using the product rule, right? So we have to pick a first element, a second element, a third element, and so on. And so the number of ways to pick the first is n, number of ways to pick the second is n minus 1, number of ways to pick the last element will just be 1. And so this is just good old n factorial. So that's maybe p of n. Now if you have n objects but you want to arrange r of them, so this is an r permutation of n objects. Right, same logic. First object comes n ways, second object comes n minus 1 ways. Right, but we're only going to have r objects that we have to pick. So it's not n factorial, it's smaller than that, right? So this turns out to be n factorial over n minus r factorial.
Do you need to understand which one to use during the exams?
Definitely. Which one of these or permutation?
Which one of the permutations?
Yeah, so if order matters, you need to use a permutation. If order does not matter, you need to use a combination. So combination is unordered. So if we're picking n objects and the order doesn't matter, there's only one way to do it. Just pick all the n objects. So normally we talk about r combinations. So the number of ways to pick r things out of n. And that's going to turn out to be the number of permutations divided by the number of orders, since we don't care about orders. And this we just write as n on top of r. So when you're doing these problems on the test, right, if you're not sure if order matters or not, right, you can ask, because maybe it's a question I'll answer. So I used to always put a pizza question on this, and nobody could handle the pizza question, so I don't have pizza questions anymore. But people would think that the order of the toppings mattered. And maybe in some sense it does if you like put the pepperoni down underneath the mushrooms. That's, you know, different from, so, but if you're not sure if I'm interested in order, you can always ask, right? And I may say you need to figure it out, or I may tell you because it might be confusing like pizza. But if you're not sure if order matters, right, put a note down. What?
The cheese has to go first.
Cheese has to go first, yeah, but some toppings burn.
Oh, yes.
Yeah.
I mean, what if you put tomato sauce on the sauce with
We should do that, yeah. They could have like random day at Domino's where they just give you a random order.
Put tomato sauce on top.
Or you could like gradiate it. On this side you could have the sauce on top, and on that side it's on the bottom. And the topping's like, anyway, yeah.
That happen when end of year comes.
Yeah. So if you're not sure, you can always put a note, right? Just make sure I can read it and say, I'm not sure if order matters or not, right? If it does, then I would use permutations, but I think that it's unordered, so I'm using combinations, right? And when you're doing this kind of stuff, right, if you say my answer should be C 5, 3 equals, and then you show me what that's equal to, if your calculations go awry, but I see this, I'm happy, right? You'll lose a point if you make a math error, maybe. Maybe you won't even lose a point, right? But if I just see a bunch of numbers multiplied together and an answer that I don't recognize, and I can't easily tell that you were trying to do a combination or a permutation or a sum of permutations or something, right? It's harder to give credit. So it never hurts to sort of like, you know, so I'm going to do P of 5, 3 plus 2 times C of 1, 1, right? Or something like that, just so I can, you know, follow your thinking, basically. Because these problems in particular, there's lots of ways to like make mistakes, and I would much rather see this, right, and maybe something like this. That's not the right value, but you know, something like that, and then, you know, the number that turns out to be wrong, but I can see that you knew how to get there, right? That's fine. So show your work within reason, right? You don't have to show every single detail, but enough to let me follow your thinking, basically. Particularly if you're not sure if you're going down the right path. All right, what else?
What specifically are you going to look for in terms of graphs?
I think what's on here. So the notion of vertices and edges, directed versus undirected, simple, which means a single edge between vertices. Degree of vertices, definitely know about that, right? So the number of edges connected to a vertex, that's the degree. If it's a directed graph, there's an in degree and an out degree. In is the number of edges going in, out degree is the number of edges going out. Okay. Know what an adjacency matrix is, right? So you have vertices on both dimensions, and you put a 1 if those vertices are adjacent to each other, if there's an edge connecting them, basically. Isomorphisms of graphs, so you had a homework question on that. That was one of the questions I graded. So if you can find a mapping from vertices to vertices, one-to-one onto mapping, right, that preserves adjacency, then those graphs are isomorphic, so they can be changed into one another. And then Euler paths and Euler circuits and Hamilton paths and Hamilton circuits. Right, so an Euler path travels along each edge exactly once. A Hamilton path visits each vertex exactly once. And there's a criteria for the existence of Euler paths and circuits. What's the rule for when we have an Euler path? What has to be true? Yeah, no. It was a long time ago.
One way.
It's a circuit and you pick every vertex.
So there's a rule that we can use to know if such a thing exists. And I always come back to the house drawing.
Isn't it if it's an even numbered circuit or something like that?
Yeah, so look at the degree of the vertices. There's my beautiful drawing. So look at the degrees of the vertices, right? If you have exactly two vertices with odd degree, you can find an Euler path. If you have no vertices with odd degree, then you can find an Euler circuit, which is also a path. So the house works because it's got two odd degrees, so you can start at any one of those and find a path that hits all the edges. And then Dijkstra's algorithm.
So Turing machines are going to be on the exam?
Turing machines will be on, I think I said they won't be.
Yeah, I think you said no.
Yeah, so no Turing machines. But grammars, languages, state machines, phrase structure grammars. Yeah, take Turing machines off that list.
Turing machines not on final.
Okay, take it off the list.
What would be the format of these things?
10 pages, 10 questions. Similar in feel to the midterm, basically. Just more topics. So, okay, so set theory, right? Basic definitions, operations, union, intersection, complements. You did this in your programming assignments, so you're extra familiar with these things you do to sets. Example, so Z are the integers, Q is the rational numbers, R are the real numbers. Those are our main.
Oh, Q is rational.
Q is rational for some reason. R is real. Yeah. Reals are more popular, so they get the R. Subsets are just collections of elements of the original set. Power set is the collection of all subsets, so the power set is a set itself. And Cartesian products are...
Q is irrational? Or
Q is rational. I don't think there's a symbol for the irrationals, but it would be R minus Q. So Cartesian products is just all the combinations of things from the first set paired with something from the second set. So it's still a set, but the elements are these ordered pairs. Bless you. So there's the Cartesian product of those two sets. And they could be infinite sets. If they're finite sets, then the number of things here is just the product of the number of things here, which isn't startling. So that's Cartesian product. And set identities look a lot like Boolean logic identities. So it's all this kind of stuff like A union A is equal to A. A union the empty set is equal to A union the universe is equal to the universe, and so on. A intersect A equals A intersect the empty set equals the empty set, and so on. Things like commutativity, associativity, distribution, and of course, good old De Morgan, which comes in two flavors. I don't know if that's true. That hurts my brain. But there's an absorption property. I think that's just A.
Yeah.
All right, so that's functions. We did injective, surjective, bijective. So domain is the space of things that you're mapping from. Range is a space of things that you map to. I don't test you on that terminology, but there is a little ambiguity between range and codomain. But mostly we care about range. Range is the set of things that your functions actually map to. So if we have something like f of x equals x squared, and let's say f goes from integers to integers, and it takes x to x squared. So the domain is the set of integers. The range is the set 0, 1, 4, 9, 16, and so on. It's a set of things that get mapped to. This z over here, this is called the codomain. But it's not as interesting as the range. It's just the space that you're going into. You can go into the space of everything, but you only actually map to these things. That's the range. But I don't test you on that, because like I say, there's some ambiguity out there. And requirements to be well defined, basically you need to know that if you take one particular x, it maps to a particular thing over here. It can't be the case that f of 5 could be both, 25 and 17. That's not a function, right? Vertical line test. So a classic example of something that's not a function is the pure square root function. Because square root of 25 is both 5 and negative 5, right? So the thing has two values. It's not a function. But if you do the positive square root, that is. Summation, you've done homeworks on those, so right, just the sigma thing, and if they're nested, just sum the inside thing first and then sum the outside thing. Matrices, that was another question I graded on your last homework, was matrix multiplication. But not a lot to say about matrices. Propositional logic, so kind of like set theory. So conjunction is an and, disjunction is an or. Inference is something like P implies Q. And then there's page 57 and 58 in the text that are the rules of inference and logical equivalences. So all that implies, quantifiers are, for all, and there exists. And most of those you can kind of reason your way through by just the meaning of those. And fallacies, so a pair of fallacies, a pair of truths. Alright, so this is direct reasoning. P implies Q, P therefore Q. That's perfectly fine, that's direct reasoning. P implies Q, not Q, therefore not P, that's indirect reasoning. Right, direct contrapositive. P implies Q, Q therefore P, that's a fallacy of affirming the conclusion. Right, if P then Q, hey, the conclusion's true, so P must be true, that's not logically true. And if P then Q, not P, therefore not Q, that's a fallacy of denying the hypothesis. Okay, those are your four corners of argument. These are good ones if you want to like prove lots of strange things, but they're not valid. Alright, so we talked a little about direct and indirect proofs. We worked with even and odd numbers. Working from what you know to what you don't know, right? So main thing to remember with a proof is, two things to remember with proofs. One, every statement must be a proposition. Don't start writing n squared plus 2n plus 1 unless it's equal to something or not equal or greater than or something like that. It's got to be a proposition, right? N squared is not a proposition. N squared equals Q is a proposition, right? Assuming you've defined what Q and N are. So make sure everything is a proposition, and make sure anything that you write follows from what you've written above it. Right? If you write something that doesn't follow, it's got to be an assumption. Or it can be the first thing that you're writing, and it can be your hypothesis or something. But you can't put down something that you don't know is true and then try to argue to a true statement and say, therefore, we're done. Right? Everything's got to follow from what you know. If you're writing down something that doesn't, put it off on the side in an ignore area. Number theory, we haven't talked about number theory yet today. So definition of divisibility. And divisibility has that unfortunate symbology with it, where we write this vertical bar, so D bar N means D divides N. Which means N is divisible by D, which means N is a multiple of D, which means there's some integer that when you multiply by D you get N, etc., right? So this is D divides N. Okay, it's not N divided by D, but it says N divided by D is an integer. And all the other stuff on divisibility comes from this definition. Okay, so modular arithmetic, A congruent to B, modulo M means M divides A minus B. So that's the definition of modular equivalence, and it means that the remainder when you divide A by M is the same as the remainder when you divide B by M. Which means if you subtract A from B or B from A, the remainder when you divide by M will be 0. And this thing called the division algorithm says that if we try to write n equals something times d plus some remainder, where our remainder sits between 0 and d minus 1, right? There's a unique thing that we multiply d by to get our remainder down to this range. And there's a unique remainder for which we can write n in this form where the remainder satisfies this. So we can call this the remainder when n is divided by d, and that's the remainder we usually talk about when we're looking at modular equivalences. So we could say n is congruent to r modulo d. If you take n and you divide by d, you get a remainder of r, right? And that's the remainder we want to talk about. But the example I used in class, right, 17 is congruent to 2 modulo 3. Because it's 5 times 3 is 15 plus 2 more. But technically it's also congruent to 5, because 17 is 4 times 3, which is 12 plus 5 more, right? And it's also congruent to minus 1, because it's 6 times 3 plus minus 1, right? So technically all of these things are congruent to 17, but this is the one that we like because it's between 0 and 3 minus 1. Primes, you know what primes are. Numbers divisible by only themselves and 1. How many primes are there?
We're still counting.
Yeah, infinite number, proven by the Greeks. There's no limit to the number of primes. Greatest common divisor, Euclidean algorithm, do you want to go over that? So if you have a pair of positive integers, I don't know, give me two integers. Some reasonably big integers.
42 and 36.
I like those. Okay, so we want to find the greatest common divisor of those. So you write the larger one as something times the smaller one plus some remainder. And then you write that 36 as something times this number plus some remainder. And when you get down to a remainder of 0, this is your GCD. And if it just so happens that when you start doing this the first time, you get a 0 right away, right? That tells you that this number divides that number, so the smaller number is the GCD. Right, that's like the easiest case to find GCD is where one number's a factor of the other. And by the way, if you happen to do this in the wrong order, like 36, 42, well, 36 equals 0 times 42 plus 36. And now 42 equals 1 times 36 plus 6, and you're right back where you were before. So no harm done. That's useful when you're coding this. So that's the Euclidean algorithm for finding greatest common factor. Any two numbers do have a greatest common factor. If the GCD is 1, we say those numbers are relatively prime. And they may not be prime themselves. For example, 128 and 25 have no common factor other than 1. Right? Even though those are not prime, we would say they're relatively prime. And then modular stuff, so modular exponentiation. So we can do all these things by switching into modular equivalences. So if we want to find 17 to the 100th mod 5, I don't really want to do that, but if we did, 17 is congruent to 2 modulo 5. 17 squared is congruent to 2 squared, which is 4. 17 to the 4th is congruent to 4 squared, which is 16, which is 1. 17 to the 8th will be congruent to 1 squared, which is 1. 17 to the 16th is 1, and so on. Right, well now I made an unfortunate choice with 100. So what's 100 in binary? 64 plus 32 plus 4. So 17 to the 100th is 17 to the 64 plus 32 plus 4, which is 17 to the 64th times 17 to the 32 times 17 to the 4th. And if you look at congruences, 17 to the 64th is congruent to 1, 17 to the 32 is congruent to 1, 17 to the 4th is congruent to 1. So 17 to the 100th is congruent to 1 modulo 5. The other trick we use sometimes for exponentiation is Fermat's Little theorem, which says a to the p minus 1 is congruent to 1 modulo p, as long as a is not divisible by p. And so 17 to the 4th, I know immediately is congruent to 1 modulo 5 from Fermat's little theorem, although we found that down here also. But sometimes that lets you get a big exponent of your number if p is big, and you can start from there and scale your way up. Because basically once you know some power is congruent to 1, life gets really good. Because you can raise this to any power and it's still congruent to just 1. Right, so Fermat's little theorem gets you to that 1 point directly. Applications, we talked about parity and check digits. I don't think I have any applications on the exam. Right, your application is solving the problem and putting down the answer. And there's no cryptography, so you don't have to like crack a crypto code for me. So induction, we talked about recursive functions. Kind of like induction. So here's your classic. Here's a classic inductive function. F of n is n times f of n minus 1 for n bigger than 1, and f of 1 is equal to 1. So what function does this define? There's two ways we can go about this. The most straightforward way is to start plugging in increasing values of n. We know that f of 1 is 1. F of 2 is 2 times f of 1, which is 2. F of 3 is 3 times f of 2, which is 3 times 2 times f of 1, which is 6. F of 4 is 4 times f of 3, which is 4 times, I'm going to write this in for f of 3, 3 times 2 times f of 1, which is 24, but you can see what's happening here, right? We're just calculating factorials. So our hypothesis is f of n is equal to n factorial. Can we prove that? I'll give you a hint, yes. How do we prove that? 2 words. Mathematical induction, right? How do we prove f of n is equal to n factorial? Make a proposition. P of n is the proposition that f of n is equal to n factorial. Our base case is P of 1. Is f of 1 equal to 1 factorial? Yes, because we've been told that. And then we need to prove that P of n implies P of n plus 1. Well, P of n says f of n equals n factorial. And I've been told f of anything is equal to anything times f of the previous thing. So from our definition of f, I know that f of n plus 1 is equal to n plus 1 times f of n. And by my inductive hypothesis, f of n is n factorial, so this is equal to n plus 1 times n factorial, and I know this is equal to n plus 1 factorial. So using our original recursive definition and our knowledge of factorials, we've proven that if f of n is n factorial, f of n plus 1 is n plus 1 factorial. In other words, assuming P of n, we've proven P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. So if we have a formula that solves a recursive function, we can prove that by using induction. Right? Again, it's all related. All right, and then the last thing on the review is pigeonhole principle, and that's just a counting argument. If you have n bags and n plus 1 objects, you're going to end up with at least one bag that has 2 or more objects in it. And that manifest itself in various ways, some of them strange, some of them pretty straightforward. If it comes up on the exam, it'll be one of the straightforward ones. So. But here's a classic combination. I did not put this on the exam because when I put this on an exam before, everybody stumbled over it. But suppose you have, let's do the same thing again with the sandwich. 3 types of breads, 4 meats, and 20 types of cheeses, because we're in Switzerland. And you want to make a sandwich, and your sandwich is required to have bread, meat, and cheese. Okay? And the question is, how many people can go to lunch without any 2 people having to order the same sandwich? Right? So that's a pigeonhole principle wrapped around a product rule. So how many students can go to lunch without any 2 students having to order the same sandwich? Well, the first thing you do is you figure out how many sandwiches there are, and there's 240 sandwiches possible. And the pigeonhole principle tells you that if there are 241 students and only 240 types of sandwiches, at least 2 students will order the same type of sandwich. Right? If there's 240 students, it's possible they could each order a different sandwich. So the largest number of students that could eat without redundancy would be 240. Or the number of students that would force 2 people to order the same sandwich would be 241. So that's a way pigeonhole can come up. But I didn't put that on there. All right, and then we talked about product rule, graphs, and grammars, and languages. I don't know if we want to say anything about those. We were doing them for the past week. And no Turing machines.
What do you want us to know about Pascal triangle?
Oh, it's good to know in general, but so if you can do that, you can do the rest of Pascal's triangle,
Yeah.
right? Because you just replicate that, and the things in the middle just add up the stuff above it. And this is just some combination, right? So first, second, third, fourth row, first, second, third entry. So this is 4, 3. Actually, I'm off by 1. It's 3, 2. Because we start from 0. But the entries in Pascal's triangle are the number of combinations. That's all you'll need for this, but there's other properties of this we went over. You don't have to know those. But they make for good party favors. All right, well, you're good to go. I'll see you Monday or Wednesday for 224 for most of you, and then I'll see you for 215 Monday. Noon on Monday. Don't come at noon on Wednesday because you missed it.
But that's at 11, right? Normal time?
Sorry?
Well, Wednesdays, normal time, 11.
Uh,
Yeah, I think they start having good changes.
I
Wait, no, it doesn't. Yeah, we used to just.
had to double check to make absolutely sure because I thought it was at 12, but I
Did you post it on
Yeah,
the?
but